Hi guys, and welcome to another marine science video. This is the second in our series. You guys are busy preparing your presentations about different zones in the sea, and so I thought I would make a quick little review video just to hammer home the idea that the different regions of the sea are really at the crossroads or the intersection of how far away we are from land, how deep the water column is, and then whether or not you are in contact with the bottom, and maybe even what kind of seafloor bottom we're talking about. So one way of viewing this very quick video is to think about the intersection of depth, distance from land, and contact with the seafloor. So nearshore environments is where we're going to start, and the intertidal zone is perhaps the most familiar to us. The intertidal zone is that zone from what we call the subtidal or sublittoral. That's the very edge of the lowest low tide, all the way up to the very highest high tide. And so these organisms that live here run the risk of exposure at some time during the tidal cycle. They may heat up over the course of the day. The salinity profile in tidal pools will change over time. And the pounding surf, of course, is a big issue too. Even in the subtidal, where tidal forces churn up the water, that's a big issue as well. So estuaries are drowned rivers, and I told you that I did some work in the Chesapeake Bay, so I thought I'd give a picture of the Chesapeake. And you can see all of these rivers that flow into this larger body. And interestingly enough, although down here by the Chesapeake Bay Bridge Tunnel, the ocean enters the bay, each of these rivers then become tidally influenced. So as the tide rises, seawater floods these rivers. And so over time, there is a change in the way the river looks in terms of its salinity profile and its depth. So here's a picture of an estuary with fringing marsh area. And over time, these sandbars may get inundated with flooding tidal waters. And so if you're stuck to the bottom, as an example, you have to be able to withstand salinity changes that will take place there. Another nearshore system that we're probably really familiar with would be coral reefs. I really enjoy this picture here showing a fringing reef and how shallow it is, and then how much deeper the water is just outside there. It kind of faces a cliff wall. This picture shows the connection really and how this system must be in what we call the photic zone. These are animals that are actually dependent upon the sun. A good amount of the nutrition that coral reef organisms gain doesn't just come from actively feeding, it comes from harboring photosynthetic organisms inside them. And you may know that coral bleaching is a big issue. Of course, these are places that we flock to because they're so colorful and neat to see. They are threatened, in part because of our visits and also because climate factors sometimes push them outside of those tolerance zones that we've talked about. Okay, so somebody's got to do the continental shelves and the neritic zone. And so I'm interested here in both the benthos, that's the bottom, and the water column. So the continental shelves are tremendously productive areas. I'm going to sneeze. Excuse me. And so here we have our intertidal zone, and then we have the sloping continent coming off called the continental shelf. And to about 200 meters or so, and that's a mark that's pretty much the same worldwide, the slope of the continent changes and then it markedly begins to drop off. So we're talking about this area right here called the neritic zone. The neritic zone is actually the water column that stands above the seafloor there. And here you can see this is the Caribbean Sea, or excuse me, the Gulf of Mexico, and you can see the continental shelf here. You can see the margin of the continent, and you can see this relatively shallow area that's highlighted in light blue, and then the precipitous drop that takes place just a little bit off. And so that's this area right here. And because the entire area is within the photic zone and gets plenty of light, because it's shallow and is tidally mixed, nutrients are always churning. These are tremendously productive areas, and of course runoff from land supports the nutrient load. Okay, well, how about the pelagic zone then? So the majority of the ocean is really out here in this oceanic zone. And we think of the pelagic zone as being that water column at depth. So part of the pelagic zone includes this little layer, the photic zone, which I think is really shown too deep in this picture. The photic zone worldwide goes only to about 200 meters or so, and sometimes more shallow depending on what lives there. And then we have this vast depth of water column. It's far away from a continent. The light is dimming as we go down, and typically, because it's the oceanic zone, we're far away from the continent and nutrient loading. So we might go out fishing, and if we were to drop down, and we would see that it would get increasingly dark. The pressure, of course, would increase. And so this becomes niche habitat for different kinds of organisms. The pelagic zone, just like the neritic, the pelagic really refers to the water column. And so if I live in the pelagic, I'm really not in contact with the ocean floor. Okay, so if we get all the way to the deep, deep ocean, let's talk about what's on the bottom. And if we were to take a count of what lives there, up in this epipelagic photic zone, we would find huge amounts of biomass. This is where the most productivity is because it's really warm and it's abundantly lit. But as we drop down and the light diminishes, we see a pretty steady drop-off here in biomass. And then when we get all the way down to the seafloor, which is really far removed from any light source, we actually see an increase in biomass in the deep waters. That's kind of cool. So why is that? Well, if I were to dig up the sediments, a good portion of that biomass would be microbial. Living within the sediments, I would find lots of different kinds of bacteria, some filamentous, that take up that space. I would actually find creatures that live on and in the substrate at great depth. And then you're probably familiar with these out-of-world pictures, science fiction-like pictures of different organisms, like an anglerfish, which would have a lure. This is a giant isopod, a salp. This is an octopoid. So the diversity and richness of these communities goes up, in big part because now we have a different type of environment to live in, and we know that the seafloor is uneven and variable, so organisms can live on it and within it. Okay, relatively new to science is the hydrothermal vent communities. So if I were to look at a map of the world, we would find that it's really carved up into puzzle pieces, and those puzzle pieces denote active areas of faults and volcanic activity in spreading centers. And so this map is showing a series of red dots and blue dots that are indicating where hydrothermal vent communities have been found and studied. Not surprisingly, there's one here in what we call the African Rift Valleys, a spreading center here. So what's going on? Well, when new oceanic crust is made and hot magma comes up and pushes to the side the seafloor, some of that water is percolating through these metal-rich sediments and comes and gets fused with this hot magma. It becomes superheated, look at that, 350 degrees Celsius, and is forced out. And look at this rich mineral assemblage that comes out with it. Now for you and I, that would be quite toxic. The idea of having a chimney in your backyard probably isn't a very good idea. But what's really interesting is that when we go down there and we see these chimneys with iron and sulfur-rich smoke, we also find very rich assemblages of life. Much greater density than we would expect at that depth or given that topography. And the submarine Alvin, I think it was 1979, was the first to see these vent communities. So, interestingly enough, these are communities that are detached from the sun and do not derive their nutrition from solar input. Okay, so I think that's all of our areas that we wanted to talk about. So here's my last slide just as an overview. You can see how light is a diminishing resource as we go down from depth. You can see that as we move away from the continents, actually quite rapidly, ocean depth increases. And so the living space that's not in contact with the seafloor gets bigger and bigger. That becomes a larger and larger volume. And not surprisingly, it's up here in shallow waters that are well lit and connected to continents where the greatest productivity happens. So here's our remembering what we want to remember. Depth, well, we talk about depth because it talks about light, the pressure that organisms are experiencing, whether or not they're experiencing wave action or if the tide would move away and they become exposed. And then, of course, temperature changes, and there may be salinity changes too. Distance from land is really important because that's a source of nutrients for primary productivity. And then contact with the bottom, well, that's expanded living space. I don't necessarily have to swim. I could live between the sand grains. I could live on that surface. And so the types of life that can live when the water column is in contact with the bottom are much greater than when it's just the water column by itself. So I look forward to your presentations, and hopefully we'll come to gain a better understanding of these very different but important marine communities.